All right, let's talk about univariate distributions. In this lecture, we're going to cover the parametric distributions. We'll talk a bit about non-parametric, and I think in the next video we'll get into Monte Carlo simulation and distribution transforms. So parametric distributions. Why do we have, or why are we concerned about parametric distributions? Well, there's a variety of different parameterized PDFs and CDFs that are available for us to work with. These are distributions which have their complete CDFs and PDFs described by just a limited set of parameters. They're pretty useful for modeling, for fitting distributions. If we're trying to fit data, it's nice to have a set of PDFs and CDFs that we can work with that are quite compact. But in addition to that, these distributions often relate to underlying theory. For example, the normal distribution is the limit distribution for the central limit theorem that we'll discuss shortly. This chi-square distribution is for the resulting distribution if we take the square of a set of Gaussian distributed random variables, the Weibull distribution, and so forth. All of them, many of them have specific, are the result of specific processes, so we can expect to encounter them, and they have very nice properties which we can make use of to solve a lot of practical problems, and we'll go through those together. So there's a variety of different parameterized PDFs and CDFs that are available to use, to work with. They have useful statistical properties. When we get into the Gaussian distribution, you'll find out that once things are Gaussian, everything is Gaussian, and which means that if the overall joint distribution is Gaussian, then all marginal and conditionals are also going to be Gaussian, which is quite useful. We'll also find out that there are some distributions that commonly occur within nature, specifically the central limit theorem that we encounter whenever there's any type of an averaging type of a process, aggregation type processes result in the central, result in Gaussian type of distributions. And they encompass a range of possible assumptions. The uniform distribution provides us with a maximum uncertainty distribution. The distribution says, I don't know, I simply know the minimum and maximum value. And so with that, let's list a couple of the possible distributions that we could talk about. And these will be the ones that we'll cover during this discussion right now. Okay, the uniform distribution. If I had a die available to me and I was to roll that die, what is the probability of observing a 1 through a 6? Now, of course, my die is fair. I haven't cheated. I haven't weighted the die in any way. We would expect that there's multiple possible outcomes with that die, 6 possible outcomes, but each one of them has the same probability of occurrence. And so if I roll a die many times, I would expect that I would get results 1 through 6 with a equal probability of each possible outcome. And so that would be an example of a uniform distributed phenomenon. The PDF is simply going to be equal to 1 divided by n, where n are the total number of categories that may occur, and it will be equal to a constant. You can look at it very quickly and observe that that would in fact result in a integration under the curve of total probability equal to 1. The CDF would simply be shown here. And so we can see that the CDF is formulated by just integrating the PDF. And we could look down here and graphically observe the behavior of the PDF, the CDF, in all of its grandeur. We have a PDF that's simply level for cases 1, 2 through 6. They would all have equal probability of 1/6. And for the CDF, we would observe a straight line going from case 1 with its probability, case 2 including its probability plus the probability of the first one, and it would just rise in a linear manner. As I mentioned, the uniform distribution is considered to be a maximum uncertainty distribution. That's because all we specify is the minimum and the maximum value. Then we say that it could be anything between that range, in that range, all with equal probability. We have no additional information to try to determine a mode or anything like that. So it's a very uncertain distribution. It's also important to us because for the process of Monte Carlo simulation, we need to draw random values to sample from the distribution. We don't want to change the distribution, so we use random values that are uniform between 0 and 1 so that we do not actually change the distribution that was used in the Monte Carlo simulation. But we'll get into that. Let's talk about the binomial distribution. So the binomial distribution. In life, we have many things for which we have multiple attempts or trials, and we have two possible outcomes for every one of those attempts. We play a hockey game, and we could win or lose. This is not the regular season, this is the playoffs, you don't get to tie. You drill an exploration well, and either you have discovered a resource in the subsurface, or you have not. And so these types of phenomena are modeled well with the binomial distribution. This is the binomial distribution right here. Once again, for multiple trials. So we'll have the equation here for the PDF, the equation for the CDF. For the PDF, we have N just represents the number of trials. X is the number of successes. We'll label trials as success or failure. They could just be any two results. And P is the probability of success. X would be the number of successes. 1 minus P would be the complement, therefore the probability of failure. N minus X would therefore be the number of failures. So if you look at this equation, it's actually very interesting. We have a combinatorial or combine operator up front, which we use the binomial coefficient, might be another way to phrase it. If we want to describe it, we would say N choose X. And the equation is shown here with a bunch of factorials, a factorial in the numerator and 2 in the denominator. And if you look at it, we could give ourselves a very quick example. 3 choose 2. So if we were working with heads and tails on a coin, and we want to know all the combinations by which you could get 2 heads, 3 choose 2 would tell us that. It would tell us that there's 3 combinations by which you could get 2 heads. HHT, HTH, THH. And so you can quickly confirm this, and you could look at a variety of different examples. So what's this telling us? It's telling us the different types of scenarios by which you could get the combination of successes out of the trials. Okay, so that's the number of the combinatorial. This right here, this calculation right here, should be pretty familiar. We've talked about independence. If I want to know the probability of getting 2 heads on a coin toss, I could do that by taking the probability of heads times the probability of heads. And if heads is a success, that would be the probability of that occurring. And then let's say I was concerned about maybe 1 tails at the same time, just like this example here. I could calculate it as 0.5 to the 2 power squared, and that would be the probability of getting 2 heads. And then multiply that by 0.5 to the 1, and that would be the probability of getting 1 tails. That's assuming the coin is fair, evenly weighted. And so this part right here would be the probability of one of these combinations occurring out of all combinations. This combinatorial multiplied by it would account for the fact that there's 3 ways that that can happen. And so that put together gives us the probability of 2 heads out of 3 trials, including all the possible ways we could do it. Now you could take the binomial distribution and solve for the PDF for a range of values. And so in blue, we have the example where 50% chance of success for 20 trials. And very quickly you can see the distribution, its behavior, its shape, its mode is right at 10. That makes sense because the expectation of the number of successes would be equal to 0.5 times 20, which is equal to 10. And so that makes sense. That's right in the center of the mode, the most likely value. And you could look at a range of other values and look at the shape and so forth. So in general, just like I said before, You can use it for a variety of different situations, and we use coin tosses to illustrate this idea of exploring the combinatorial, and we can do that with coin tosses because it's 50-50. Possibility of heads and tails are both 50%. Therefore, all of these combinations of coin outcomes are all equal weighted. And so you can very quickly see that you could calculate by hand the probability of getting 2 heads out of 3 coin tosses simply by taking a frequentist approach, looking at each one of the possible combinations that may occur, recognizing that they're all equally likely, and calculating 3, which all have 2 heads and the rest do not, divided by 8, which are the total number of possible combinations. And you'd calculate 0.375, which would be 37.5%. You could take the binomial distribution and do the calculation saying, okay, probability of heads is 50%, therefore tails is, the complement is 50%. We have 2 heads, 1 tails, raise them to the right powers, put the combination or the combinatorial or the binomial coefficient calculation up front, and you get 0.125 or 12.5% probability for each one of these cases, 1 out of 8. And we would find that there's 3 possibilities by which we accomplish what the criteria of having 2 heads out of 3. And so we get 3 times 1, 0.125, and that's exactly equal to what we got when we took the frequentist approach, which once again we could do only because each one of these had equal probability. It'd be more complicated, of course, if we had heads and tails or different success rates that weren't 50%. But this is very useful to understand the need to apply the binomial coefficient up front because we have to account for the multiple possible cases by which we meet that criteria. Now, a couple more comments on the binomial coefficient. Once again, it's read as n choose x, put whatever numbers in. It represents the number of possible combinations. We show the equation here again. And it uses, of course, the factorial operator. Just a reminder for anyone who's a bit rusty on that. Also note, you can look this up. The 0 factorial is equal to 1, which might be a little bit of a surprise to you, but that's the case, and there's proofs for that too. And if you're interested, Pascal's triangle would be a visualization of all the binary coefficients, and it could extend on ad infinitum down below. And that could be kind of interesting to visualize. And we just used a couple of cases like this. 3 choose 1 example here. 3 choose 2 would be here, and so forth. So what I'll ask you to do is just go ahead, open up Excel, and try this out. You have an exploration drilling program with failure rate of 70%. Success rate would be 30%. Your company is drilling 10 new prospects. What is the probability of only 3 successful discoveries? Which still would be pretty good, in fact. Use a hint. Use Excel combin command to get the n choose x. You could also just use the binomial distribution command shown down here, or you could try it both ways. It's not bad to try it by hand. So go ahead. I'll show you the answer in 3, 2, 1. So this is the result. If you do the combin command, 10 choose 3, you'll find out very quickly there's 120 combinations by which we can get 3 successes out of 10 trials. The probability of each one of those is calculated by taking the probability of success to the power of the number of successes times the probability of failure to the power of the number of failures, and multiply that by 120, and you'll find there's a 26.7% chance of 3 successes on your exploration program. What's the probability of no success at all? That's interesting. And so you could do the combin 10 choose 0, and it makes sense. There's only one way to do that. Fail, fail, fail 10 times. Multiply that by the probability of success raised to the 0, which would be a 1. Multiply by the probability of failure raised to 10. And you're going to find out that there is a 2.8% chance of not having a single success. Okay, so that was a nice little example to demonstrate the binomial distribution. Just for fun, I went and calculated the binomial distribution for that problem. 70% chance of failure what's the total number of successes you should expect with their associated probabilities, and I plotted them up so you can see the whole range of values. Note, I could have plugged into the equation, we could have investigated 10, 9, 8, and you would have found that there are a very small probability of seeing that. That would be very lucky, 30% chance of success. And you have 10 of them in a row would be very, very lucky indeed. Now, I drew a line so you could see the shape. But I want to remind you the binomial distribution is discrete. It's only discrete. The answer is only available at 0, 1, 2, where the dots are. There is no probability available to getting 1.5, 4, 3, or some number in between the integers. Now, people might be interested in playing around more with the binomial distribution. So I put a complete example on GitHub. Here's the link right here. Just click on this link right here. Or I don't know if it's live. You might have to type it in. Put this in, go there, and you'll get this spreadsheet. And you'll get to change the probability of success for case 1 and 2. And you can immediately observe the distributions of the binomials with the probabilities of each number of successes. And in addition to that, I built the distributions for each one of those cases with the probability of having a string of failures. And I think that's very interesting. So if we take the first case with a 20% chance of success, we can go to the blue curve, and immediately you can see that you have about a 18% chance of having no successes at all in 8 tries in a row. And that's very important because a lot of people do not understand the binomial distribution, and they may be surprised to know that at a 20% success rate, you have that high, almost 20% chance of having 8 attempts with no success. In fact, most managers would probably suspect there was a problem and not realize that we were still reasonably within the distribution of possibilities if we had 8 failures in a row at that rate of success. Okay, now let's talk about volcanoes. I know I follow some volcanologists on Twitter simply because I just think it's amazing and I really enjoy the data, the geology, and the earth dynamics and so forth. But I'll get a little chance to talk about volcanoes now, maybe. Okay, so volcanoes, they're very much like what we were talking about before. They really are binary. Now, sorry, I'm sure volcanologists will correct me. There's many things they can do, but we could say they're erupting or not erupting. Something's going on active or they're dormant. Sure, I could be corrected. But what's interesting is they're not like the previous problems. The previous problems was Wayne Gretzky puts on his ice skates and he goes and plays a game. He's playing the game and he either wins or he loses the game. There are trials. There's a total number of trials and there's a number of successes or fraction of trials that result in success. But a volcano, it doesn't sit there and try to erupt and then fail. A volcano over a period of time or an interval of time will have so many occurrences of erupting. And so it's very different. Both distributions are for binary outcomes, success and failure. But the Poisson distribution is different. We're considering, the average number of successes or events happening per an interval or unit time or cycle or space or something. There's an interval we're concerned with, and we know that this happens a certain average amount of times. Now we're assuming a constant rate. In other words, the probability of it happening, the happening, is going to be uniform. It doesn't change over time or over space. It could happen just as much anywhere. They're independent. The fact it happened once doesn't affect whether or not it will happen again in the short term, the long term, or anything. They're just independent. And it's binary once again. It's happening or it's not happening. Now you compare this with the binomial distribution, where you have a probability of a success for every trial. And you want to understand the number of successes you should expect over so many trials. So you really could not use the binomial distribution for many problems for which we're concerned with rates over intervals. we need to use the Poisson distribution. And so here's the Poisson distribution right here. And its PDF is described here, quite straightforward. And the CDF, it's discrete, and it should feel like you're cheating a little bit because you kind of are. All we've done is simply said that the PDF is going to be equal to the first interval, to the current interval x, and a summation of all the previous intervals before it. So it's, yeah, that's a CDF. It's a discrete CDF, so that works. That's fine. The only parameter is lambda. And now, I found this kind of interesting, that we understand a phenomenon like this. All we need is the lambda, the average number of occurrences. There's no measure of spread. It just comes out of the problem, which is really fascinating to me. Okay, so how does it behave? Well, take a look at lambda equals 10. If the average number of events or happenings within the interval is 10, it makes sense if you look at the PDF at lambda equals 10, the mode, the mean, everything is there at 10. It's pretty symmetric and well behaved, in fact. Now, as we start to reduce the number and approach 0, like at 1, it becomes asymmetric simply because you have a boundary at 0. You can't have any fewer than 0 events. So it becomes asymmetric because it's squashed up against the 0. So let me give you a chance to have a little bit of hands-on practice with the Poisson distribution. So you're drilling. So when drilling through a specific formation, there has been an average of 3 fluid loss incidents. What is the probability of 5 fluid loss incidents in the next well? Now, hint, you can use the factorial operator, fact, or the exponentiation operator, exp, within Excel to solve this, or you could also use the Poisson dist and not do it by hand, but just use the equation for the PDF directly. Also, what is the probability of no fluid loss incidents? 2. Okay, so I'll show you the solution in 3, 2, 1. Okay, so if we do it by longhand and we plug into the equation, we'll find out very quickly when we fill in, all we've got to put in is lambda and x. Lambda is an average of 3 fluid loss incidents when we drill through that formation. And we want to know x, where x is equal to 5 fluid loss incidents. And if we go ahead and calculate that, we'll find we have about 10%. We put it directly into the Poisson distribution calculation like this, we'll get about 10% also. Now note, I set this parameter as false. That parameter explains or determines, I should say, whether or not the result is cumulative. What would happen if I put that as true? I would in fact be solving for the probability of at least 3 fluid loss incidents, including 0, 1, 2, and 3. So we didn't want to do that, we just wanted it for the 1. What is the probability of no fluid loss incident? Well, we can plug into that equation again, and we'll find out that we have a probability of about 5% of that occurring. Note, once again, 0 factorial is equal to 1. I know many people, one of my students, look at this equation and feel that that should result in infinity, but it does not. All right, so like I did before, I calculated the entire distribution, taking all possible cases from 0 to some larger number, and you can see the overall distribution shape for the Poisson distribution. Now, it's interesting because with the binomial distribution, we had 10 trials, so we really couldn't calculate it for above 10. You can't have 11 successes out of 10 trials. That would be an error, right? With the Poisson distribution, you could calculate it. There's no upper upper bound. You could calculate it for a very large number of events, but of course its probability would be dimensionally small. I have also provided a complete example with description, with information, and so forth on the Poisson distribution. For those of you interested to play around with it, you can, for case 1 and 2, you can vary the lambda, the average number of events within the interval, and you can observe the results. There's some explanations and so forth, and that's available once again on GitHub for those of you who would like the opportunity to play with this example tried out. Let's talk about the Gaussian or the normal distribution. So the Gaussian normal distribution, anytime I say Gaussian or normal, I'm talking about the same thing. The Gaussian distribution is also often denoted by an n bracket mean comma standard deviation. The brackets may vary. Sometimes you'll see round, sometimes you'll see squared brackets, but this general notation suggests the mean and the standard deviation. Sometimes you'll see people denote it by the mean and the variance, and so I show sigma squared to represent the population variance, mu for the population mean. Where is the Gaussian distribution useful? In many situations, error is Gaussian distributed. If you look at a target shooter shooting a target, you look at an estimation model, you look at many different methods where we're estimating the error is Gaussian. The summation of a property or averaging of a property, if we take a distribution of that average, tends to also be Gaussian, have a Gaussian shape, Gaussian distribution, at least it approaches it, and we'll talk about that a little bit right now. What is the equation for the Gaussian distribution? Well, we have it right here. It's shown with two parameters. We have a mean, and I've shown it as mu, the population average, and sigma, the population standard deviation. The CDF is represented through this integration. We pull the constants out, we're integrating the rest. And you notice we have not solved it. There's not a closed form solution for it. There are many good approximations available that are used widely, but the actual integration, there is not a specific solution to it. Don't try it. It's one of the worst afternoons I ever spent. The Gaussian distribution, some examples of the PDF for different mu's and standard deviations. Very nicely behaved. You can see this one right here in purple with a very, very wide variance and a mean of 0. You can see the red one with very low variance and a mean of 0. And you can look at the shape of the CDF and see immediately why people call it an S-curve. It has that kind of S-like shape to it. So more on the Gaussian distribution. Once again, we have shorthand for it. A lot of natural variation will behave in a Gaussian manner. The distribution's unbounded. There's no min or max to the Gaussian distribution. It effectively goes negative infinity to infinity. Although, just like the Poisson distribution, the upper tail, very large or very small values for the Gaussian distribution are very unlikely. And practically in most methods that use the Gaussian distribution, there'll be some form of truncation that's used to prevent the values from going to something that's very unusual, just to prevent that very random, that very unlikely use of a very large or small number. Let's talk about the central limit theorem a little bit. If we take the summation or average of multiple random variables, it will tend towards Gaussian distributed, regardless of their specific shape, which is really, really interesting. This occurs pretty quickly. Technically, it should be a large number of variables, but I'll show you an example where we have maybe 6 variables being averaged together, and that goes very quickly towards Gaussian. It looks very Gaussian. Some reservoir properties may be Gaussian distributed. We can't specifically say that they theoretically should be, but there are some variables such as porosity, which often tends to, if you have a stationary population of rock, you don't have a lot of mixing of populations, you often see Gaussian porosity. And that's because if you think about it, porosity in fact is like, take all those small values or small volumes in the reservoir with their pore and solid proportions, and now add an average over to large volumes up to the reservoir, or up to the unit or the measurement scale that you're working with. You could in fact look at porosity like an averaged parameter, and that could be considered why you tend to have a Gaussian type of distribution. Now, of course, once again, this will be disrupted if you're combining multiple facies and you have trends and so forth, so it could of course be disrupted. So let's do an exercise together. What we're going to do is we're going to fit a Gaussian distribution to this data. Now the Gaussian distribution is parameterized by mean and standard deviation. So the first step would be simply to calculate the mean and standard deviation of this data. Then you could in fact use that distribution as your fit, and now you can go ahead and calculate what is the probability of a porosity less than 18% for the very next sample that we get, given it comes from that same distribution as this data. I'll count to 3 and then I'll show you the answer. 3, 2, 1, and the answer. So when we calculate the standard deviation and the mean, we get a mean of 13.9, we get a standard deviation of 5.7, and when we use that distribution, we plug into it the when we take that distribution, take the inverse of it, plug into it the value of 18, we get back a cumulative probability of being 18% or less porosity of 76.4. Now you might be interested in what that looks like. And so what I did was I took our data and I used the cumulative probability assumption of I over n plus 1, which means I assume I don't know the tails. You'll notice that none of these data are sitting at 1 or 0. I'm assuming the tails are not sampled. And I can plot the CDF. Then what I did was I took our Gaussian distribution with a 13.9% mean and a standard deviation of 5.7%, and I plotted its CDF with our data. And when you look at that, you see, in fact, that's a pretty nice fit. That's looking pretty good, in fact. That we have a pretty good fit. Now, there's a little bit of departure, but you wouldn't be able to fit that anyway, right? Wouldn't want a distribution that was a little noisy to fit that. That'd be overfit. So the Gaussian distribution seems to describe this phenomenon pretty well. And by fitting the distribution, this is the first time we've done that, we now have a predictive model that can tell us any of the cumulative probabilities associated with the next sample that might be drawn from this distribution. Well, I mentioned that I was going to demonstrate the central limit theorem, so I thought, okay, what I've done is I took a set of random variables x1 through x2 through x6, and I calculated the average of the first one, which would be just taking that original value. Now they were all uniform 0, 1 random values, so that first one should in fact have a uniform distribution. If we look at the black points, that is the result of just one random variable. And if we try to fit it with a Gaussian distribution, which is the black curve, you can see it's a very poor fit. It doesn't work. The data is uniformly distributed. Gaussian distribution doesn't fit. And that makes sense. Then you take the case where you have 3 random variables, which is the green data set, and you fit it with the Gaussian distribution with the same mean and standard deviation of the data that we got from that random process. And what you'll find, it's not bad. On the tails, you might run into a little bit of trouble, but it's actually performing pretty well. That's only 3 variables being averaged together, and you're already getting almost a Gaussian distribution. That's really cool. If you take 6 variables and average them together, look at what's happening to the red data, which is the resulting CDF of all that data being average of 6 values. And we plot them together, and then we fit a Gaussian distribution in the red curve. We in fact get something that definitely looks very Gaussian. Now I'm sure if we were to run a test or something, we'd find there's departure, not perfect, but clearly you can see the transition of the distribution as you're averaging from 1, which is just the uniform distribution of the random values, up to averaging 6, that it's definitely becoming more Gaussian in shape. So let's think about the log normal versus the normal. A lot of people struggle with the log normal distribution the first time they hear it. The way to think about it is if you take a Gaussian distributed random variable x and you apply the exponentiation to it, it actually will become a variable y, and that variable y is going to be log normally distributed. That's pretty cool, right? Now if we take y, which came from x, and we apply the ln to it, the opposite of exponentiation to it, we get back to x. So if your log normal distribution, you apply the ln to it, you will get back to a normally distributed original variable. How do we get a log normal distribution? The Gaussian distribution came from the addition, summation, or averaging, which is really just an addition or summation, of a set of random variables of any distribution. The log normal distribution comes from the product if you take the product of random variables of any distribution, they will tend towards a log normal distribution. I have a demonstration of the log normal distribution where I go forward and back. I go from normal to log normal and back to normal again, and I show how to calculate all the parameters and so forth. If you're interested, you can try. So now let's look at the PDF and the CDF for the log normal distribution. We can see them right here. It's important to note that they are parameterized by the sigma and by mu. And what's very interesting here is that mu is the mean of the ln of the random variable. In other words, as we mentioned before, that if you take a random variable that's Gaussian distributed and you apply the exponent or exponentiate it, it will become log normal, and if you apply the ln, it will become normal again. It shows us that mu is in fact the mean of the Gaussian associated distribution with the log normal distribution. And the same thing for sigma. Sigma is the standard deviation of the ln of the random variable x, therefore the Gaussian associated distribution. And so what's very interesting is that log normal parameters are not of the log normal distribution, but of the associated Gaussian distribution, which a lot of people find a little bit confusing. I'll show you how to move back and forth between them. But here's the equations for the PDF for the log normal distribution. Once again, for the CDF, we have an integration here because there's not a closed form solution to it. We can look visually at the log normal distribution, and immediately we see that there is a very strong positive skew to the log normal distribution. We have this tail that goes out on the positive side, and that the S curve in the CDF has also been dramatically skewed. You can see this long tail right here. So it's important to be able to move back and forth, because if we want to work with the log normal distribution, we would want to actually know for a given set of parameters mu and sigma what the central tendency will be, the expectation of the distribution, and the spread, the variance of the distribution. And so you can see here that once you've selected your parameters for your log normal distribution, you can substitute them directly in. First of all, you would calculate the expectation by taking mu and sigma in this equation here. Once you have the expectation, you can populate it in this equation right here along with sigma, and you can calculate the variance of the distribution. Of course, you may want to even move the other way, which means that you know the mean and you know the expectation and you know the standard deviation of your distribution, that's log normal, and you want to solve for what mu and sigma parameters you should be applying. And so these are the equations right here in order to calculate mu and sigma that you would then put into this equation, that you would parameterize your log normal distribution. If you wanted to calculate the expectation, the variance of your sample set, you could then calculate sigma mu to fit a log normal distribution to that data set. So now what we'll do is I'll give you a chance to do that. Go ahead and you have permeability in your reservoir that is log normally distributed, which is pretty common, with a mu equal to 2.0 and a sigma equal to 1.8. Now calculate what is the central tendency, what is the mean or expected value, and the standard deviation, a measure of spread of that distribution. Use the equation on the previous slide. Once you've done that, go ahead and calculate what's the probability of having a permeability less than 100 millidarcies. For that, you can directly use the log norm disk function in order to calculate the cumulative probability. I'll give you I will give you the answer in 3 seconds. 3, 2, 1. So we just used the previous equations. First we calculate the expectation given mu equal to 2.0, given sigma equal to 1.8, and that gives us a expectation of 37.3 millidarcies. Now we have that, we can put it into the equation for standard deviation, and we get a standard deviation of 184 millidarcies. Now what's the probability of permeability less than 100 millidarcies? We can use the log norm disk command, and we can calculate that that should be about 93%. If you're curious, to look at this distribution and just see what it looks like in general, I went ahead and took the mu and sigma and calculated a complete table of cumulative probability values in order to display the CDF for our distribution from our data. And so if you look at it, it has this type of shape, and you might be surprised. We're back to having a nice S-curve shape. If you look closely, what you'll see is I'm using a log scale for the x-axis for the values. And so effectively, if you work with an x-axis that's in log scale, you will once again get the Gaussian or normal shape for the CDF or PDF, depending on which you're looking at. So there it is. We could check our answer. We had about 100 millidarcies. If you come up here, you could be convinced it's actually, we could look it up right here. And so by the time we get up to about 100, we're dealing with something that's close to on the order of about, about 93 or so %. That makes sense. Things look okay. The log normal versus the normal distribution. I have a file on GitHub. Here's the link right here, where I start with percentiles going between almost 0 to 1. I calculate a standard normal distribution. I scale it to have a target mu and sigma, mean and standard deviation, in the normal space. I exponentiate that value in order to get a log normal distribution with the right mu and sigma. I even check the mu and sigma and make sure it's correct. Then I go ahead and I use the Excel function with the mu and sigma, and I find I get exactly the same distribution back. So I've done this right. I have the right mu and sigma. Then I apply the ln to this, and I get back to the Gaussian distribution shown here. And I go ahead and normalize it to have a mean of 0, a standard deviation of 1, and I close the loop. I've gone all the way from a standard normal Gaussian distribution to a non-standard Gaussian distribution with mu and sigma for mean and standard deviation, to log normal, to comparing with the log normal function directly from Excel with the same mu and sigma, to going ahead and taking the ln and going back to Gaussian, and then normalizing it with an affine correction to get it back to the mean of 0 and a standard deviation of 1. And I check what would I expect from the equations as far as the mean and the standard deviation. And I actually calculate the mean and standard deviation directly from the table, and I make a comparison there. And so I close the loop. So if there's any questions about log normal, how to go back and forth, how to calculate the parameters, this should definitely help you with that. Let's talk about student t distribution. We're going to go through a couple more distributions a little more quickly. We won't go into too much detail because, to be honest, these distributions are much more interesting from the perspective of what we can do with them. So we'll comment on them, not go too much into them. Student t distribution, the PDF is shown here. The phi symbol is simply going to be the degrees of freedom, which would be n-1. We have a gamma function that's being used twice here. The gamma function equation is shown right here. There's other forms that are shown elsewhere. I won't get into the details on the gamma function, but let's just take that to be the student t distribution. Now, what's more important is where's it derived and how can we use it? If we take the mean of n independent random variables, all from an identically distributed Gaussian distribution where the standard deviation is not necessarily known, that will be student t distributed. So that's pretty powerful. So let me just rephrase that. Take n samples from Gaussian distribution with unknown standard deviation. They all have the same standard deviation, but not necessarily known. If you calculate the mean and you repeat, the means will have a student t distribution. And the type of student t distribution will depend on the number of random variables that you're averaging, the degrees of freedom, n-1 shown here. As phi, the degrees of freedom, goes to infinity, the student t distribution approaches the normal distribution. So that means as that sample size that you're averaging over goes large, it will go towards Gaussian. Here's a set of examples taken directly from Wikipedia, where we have different degrees of freedom. At infinity, the black line is a PDF of a Gaussian distribution. And at 1, we have When we have only one data, which is very few, we have that. Which would be two data, n minus 1, of course. And if we have a case where we have degrees of freedom equal to 5, it converges more towards the Gaussian. So what's the difference? The student t distribution helps you out when you have too few samples in order to expect reasonably for your distribution to approach Gaussian. At that point, what happens if you have too few samples is, in fact, the kurtosis starts to become negative. It would probably be platykurtic because you have fat tails and you have less peakedness going on. And so that's really the difference, is that when you have too few samples, you tend to have your mean is distributed with fatter tails. We will use the student t whenever we have too few samples, and also when the population standard deviation is not known. We're going to use it in all kinds of places, but specifically right away in the test of the difference of means between two sample sets. That's where we'll commonly use it. The chi-square distribution. See, I told you we're going pretty quick through these. The chi-square distribution, the equation is shown right here. Once again, phi is the degrees of freedom. We've got a lambda function again. If we have random functions x1 through random variables x1 through xn, and they're independent, identically distributed, and they're all Gaussian distributed, the distribution of the sum of squares of this will have a chi-square distribution. Now this is pretty useful. The sum of squares is used in a lot of different applications, and so if you even think about it, a variance is the sum of squares and so forth. And so we could use this for a lot of our hypothesis testing. For instance, comparing two distributions or CDFs, and we'll show that. Here's the chi-square PDF and CDF for different degrees of freedom. You can see it's got a very interesting shape to it. The Fisher's F distribution is shown right here. The equation is right there. And this is interesting because the way it works is if we have two different data sets, two different random variables, and we're taking the ratio of them, and they're both chi-square distributed random variables, then we would expect that they would have the ratio would have Fisher's F distribution. It would be Fisher's F distributed with this PDF shown right here. These are the images of shapes where we're looking at different amounts of degrees of freedom. For the first component, phi 1 and phi 2 are shown here, and we can look at the general distribution. Where do we use this? When we're doing an analysis of difference in variances, we'll take the ratios of the variances, and that will be Fisher's F distributed, and we'll use it there. There is also a whole general family of distributions that could be used, linear family of distributions. If you take a CDF or set of CDFs, 1 through k, and you apply weights to them, the weights would sum to 1, and the weights would always be greater than or equal to 0 for all possible k categories. That in itself would also be a licit, it would be a valid CDF. And so here's an example below where we took multiple distributions and we combined them together. These become mixture distributions, and so these could be CDFs we could work with, and they would be parametric. They would have multiple parameters representing each one of the combined CDFs that are linearly being weighted and combined together. We could also consider general non-parametric distributions. And so there's really no need to assume a parametric form. It's convenient because it's compact. You can use just a couple of parameters to describe the entire behavior. There's theoretical reasons to work with certain distributions that can help us with hypothesis testing and even prediction in natural settings. But if you have enough data, you can simply order the data in ascending order, calculate the cumulative probabilities, and just go ahead and calculate the CDF directly. In fact, and you can also later then transform any distribution to any other distribution. So you always have that opportunity to work with raw data and to formulate your own CDFs and to be able to transform between possible distributions. Now I'm going to leave this video right here. I'm not going to go into Monte Carlo simulation. We'll cover that next time. But as always, if you have any suggestions, comments, I hope these videos are helpful to you. To my students, I hope you're enjoying the GeoStats class. Let me know if there's anything I can do to make it more interesting. I'm always looking to make it a more interesting, fun class for you all. All right, thank you very much. Bye.